Hello, welcome everybody to session 2A on future roads and mobility, basically the same topic that the overall theme of the Congress. My name is Hwt Gomez. I'm the Technical Director of the European Asphalt Pavement Association, and it will be my pleasure today to be chairing this interesting session. We will start with a brief keynote from Christophe Nicodème. He is the Director General of the European Union Road Federation, ERF, and he will explain a bit what is the concept of infrastructure 4.0 and how the new mobility can impact on our road infrastructures. Then we will have a series of presentations on different disruptive innovations, which nowadays are already changing our sector very fast. For example, just 10 years ago, a group of scientists received a Nobel Award for the main breakthrough on a material that we all know, which is graphene. And nowadays we already have the first implementations on real roads with asphalt containing graphene. We will hear about that. We will also see a series of technologies that we are having now, such as, for example, energy harvesting or systems embedded in the road for self-monitoring, which without doubt will help us to deliver a greater customer experience for our clients. The session will be structured in two parts. We will have first 3 presentations with a 10 minutes Q&A, and then we will have other 3 presentations with the final 10 minutes Q&A. I encourage you to use the text box that you have for the comments and for questions. If you are referring to a specific speaker, please include the name of this speaker so I will know to whom should I address. Also, you can like different questions and comments. That will help me as well to identify those that are most interesting for the audience. Speakers will not answer questions in this chat box, so we will discuss about that orally during the Q&A. With all this, I think that's it. I'm very excited of presenting the first speaker. He is Christophe Nicodème, Director General of ERF. He graduated in translation, and after an intensive training in sales and marketing, he started his career working as sales manager for companies specialized in the road infrastructure sector, more particularly for road markings, road maintenance, and road safety systems. He comes with an international experience in implementing and assessing traffic calming schemes in urban areas and on major road networks in Europe and Latin America. Nowadays, he is the Director General of the European Union Road Federation, ERF, a non-profit organization representing the European road infrastructure sector and acting as a platform of dialogue and research for road mobility issues. Christophe, it's our honor having you here today for this introductory keynote. Please, the virtual stage is yours.
Good afternoon, ladies and gentlemen. My name is Christophe Nicodème, and I'm the Director General of the European Union Road Federation. And I'm particularly honored to deliver today this keynote for the opening of the technical session on future roads and mobility. To be quite honest, when I was asked to provide a title for my keynote, I thought, well, why not Road Infrastructure 4.0 in relation to the general title of the E&E Congress, Asphalt 4.0, with an obvious link to mobility. Then, after that, I must say that despite much research on my side, I could hardly find a definition of Road Infrastructure 4.0. I was quite disappointed. So what could be Road Infrastructure 4.0? Will it be a new generation of physical infrastructure with some changes compared to the current one? Or just an evolution of the traditional one with more digital elements? Or something just the basics with full of digital elements like markings, signs, barriers, and just the surface being there and the rest being provided by virtual and electronic connection? These are many questions, and obviously we don't have the answers. But one thing is definitely sure, is that road infrastructure is definitely linked to mobility. There is no mobility without roads, and roads are really at the core of mobility. And we just have to see that most of passenger and freight mobility depend on roads. If we take the example of Europe, for passenger, we are talking about 80%, around 80%, and freight mobility is around 70% insured by roads. And this is what happens in normal times, but also in critical moments, and the trend goes to an increase of that share of mobility. And when I was talking about critical moments, obviously, I was talking about the times of COVID crisis and the lockdown. And what we saw, and this is really something very specific to the road, is that during these critical moments, road could ensure an efficient, safe, and quick delivery of all the essential goods and services to all citizens, including to the most remote areas. And this could guarantee the mobility also for emergency services and for urgent interventions. Really, we see that the roads were the main support of mobility. But this was a particular moment. But even before the COVID-19 pandemic and the lockdowns moments, we could notice a change in mobility patterns, mobility usages and behaviors with the emergence of new mobility patterns. For example, it's quite known, connected and autonomous mobility, electric or carbon-free mobility, and very specifically specific to urban areas, soft and active mobility, which developed quite a lot in the last years. Based on these changes and these developments, we wanted to see what could be the impact for the road infrastructure. And this is the reason why the ERF, in partnership with different organizations, SICA, FNTP, FIAC, and Route de France, we have decided to initiate in 2019 an international benchmark study over 20 countries in the world to analyze and try to identify what would be the impact of this new mobility uses on the road infrastructure and its equipment. And again, I remind that this decision was made before the crisis linked to COVID-19. I'm not going to expand so much on that, but there were some very interesting first findings regarding, for example, in Europe, a disparate integration of new mobility with a large difference between northern countries and like Scandinavia, Germany, UK, and other EU countries in terms of approach and intervention of the authorities, for example. But generally speaking, in Europe, we are more talking about adapting existing road facilities. We see also the importance of the different roles of public authorities and differences between the United States, Asia, and Europe. A strong public support in Asia, in particular in China, where a lot of new constructions already incorporate new digital elements with a strong support from the state, and also different approach regarding the place of the road infrastructure and the difference of visions between America, Asia, and Europe, and also different expectations from the users. For Europe, what we could find really is that we saw that the role of road infrastructure was generally underestimated, despite its essential role to enable new mobility, and despite the fact that the road has to comply also with the new conditions of ecological and energy transition, which are the priorities from the Green Deal. And another interesting element was the adaptation and the maintenance of the existing road infrastructure, which is a real prerequisite to develop new mobility, but this requires a high and significant level of public investment to accompany the change, to go with it, even to anticipate it, and this has to be now considered also within the framework of the European Recovery Plan. This benchmark study, as I said, was published last year, and this is the cover of this study, which is freely available from our website. Then we found ourselves a little bit frustrated after this first benchmark study, and we saw that new behaviors appeared, particularly linked to the COVID crisis, like teleworking, less cars in urban areas, a booming of the development of soft mobilities with new cycle lanes being constructed and installed in a couple of weeks, a rise of digital technologies and growing importance and focus on the climate issues. So the post-COVID environment and the road infrastructure, all this combination gave us some new perspectives for land transports and operators considering the National Recovery and Resilience Plans. So we decided to went for a second phase of this benchmark study, which will be published by the end of June this year. Let's come back. This was a little detail on this benchmark, but generally speaking, what we see is that road infrastructure and new mobility will definitely be linked. And whatever happens, whatever the change are going to be, we will need to have an infrastructure that will adapt with a lot of flexibility to new mobility usages and quickly, that should be resilient to the climate change, that will be more and more connected, even while not self-healing in some cases, will be able to cope with different types of functions. We might also consider that the road could supply some energy. It should be greener and it should definitely be user-friendly. And when I say that, it's quite important because we will have to consider connected users, but also non-connected users. And the road infrastructure will have to keep on providing the same level of service for all types of road users. This relay requires a lot of investment for preserving, improving, upgrading, maintaining the road infrastructure, make it ready for the future with a long-term vision from the road operators. And really, as long as there are vehicles and people using land transport, the road infrastructure will need to be there. Maybe with different forms, maybe with more virtual elements, but an infrastructure is necessary. And you see at the end, I say, unless our vehicles will stop driving and they will just fly. And I found these, especially the picture on the right, very funny because this was a vision from the 1950s of what could be the car of the future, very futuristic American way of life vision. But even though if these cars will fly, this might not avoid some issues sometimes. And when I was preparing this presentation, I really remember a comic strip that I read when I was a kid. And this was the history of a guy inventing a car that could fly or be suspended and move suspended over the road. But there was one big issue, is that the car didn't have brake. So you see what can happen even in this particular case, when the car takes a forbidden direction street, no connection between a traditional user, new types of user, the infrastructure is not prepared, the vehicle is not prepared. So anyway, the infrastructure will need to keep on providing the necessary service for all kinds of users in the future. I thank you very much for your attention, and I wish you a very interesting Congress. Thank you.
Thank you very much, Christoph. I'm having right now a problem with my camera. In any case, I will introduce the next speaker. He is Taher Kalandari, and he will present the paper, The Use of Large-Scale Prototypes to Investigate the Actual Performance of a Heat-Exchanging Asphalt Layer. Taher is an academic assistant and PhD researcher in the Construction Engineering Department of the University of Antwerp, Belgium. He is working in the research group Energy and Materials in Infrastructure and Buildings. His research subject is heat exchange asphalt layers, in which thermal energy is harvested from the asphalt pavement in the summertime and stored to be used in wintertime for example, the snow melting on the road surface. In addition to this, he is also interested in geotechnical engineering, numerical modeling, and engineering optimization. Today, he will present some details of a large-scale prototype constructed at the University of Antwerp in 2017 to investigate the actual performance of these heat-exchanging asphalt layers. Taher, the floor is yours.
Hello and welcome to this session. Today I will present the use of a large-scale prototype to investigate the actual performance of a heat-exchanging asphalt layer. My name is Taher Galandari. I'm a PhD student and academic assistant at the University of Antwerp in the EMIP Energy and Materials in Infrastructure and Buildings Research Group. In today's presentation, I will divide it to 4 different sections. After an introduction, I will provide you with a short description about the project, some details about the construction stage, and finally some details for the operational phase of the HEAL project. Limited energy resources such as fossil fuels resulted us to have a high demand for renewable energy sources. However, only 4% of total energy consumption in 2018 was from renewable energy sources. Solar energy is a highly potential sustainable energy source to harvest, and this energy can be extracted from asphalt pavement using a HEAL system. For those who are not familiar with the asphalt solar collector systems, I briefly give you an introduction about the working principle of HEAL system. Solar radiation will be absorbed on the surface of asphalt pavement, and the heat extraction can be done by circulating the cold fluid through the pipes. After that, we can store this extracted energy in a borehole or aquifer and use it for winter time. We can divide the studies on the heat exchange asphalt on the HEAL systems to thermal and the structural aspects. In the thermal aspects, we have advantage of providing ice or snow-free road surface, clean energy production, and mitigating the development of urban heat island effect. On the other side, we can control the seasonal changes in pavement temperature, decrease the potential of pavement distress, and all of these result in an increase in the service life of the asphalt pavement. For the description of the project, the Cycle Pavement Technologies or CyPaths project has 5 innovative technologies within sustainable asphalt pavement. This project was constructed in 2017 in a bicycle path next to Campus Huronenburger at University of Antwerp. And the HEAL project is one of these 5 technologies. As you can see in the picture, the total area of the HEAL project with 2 reference sections is almost 65 meters square. And the pavement solar collector system is approximately 30 meters square. In the construction stage, we used asphalt pavement is a dense mixture. Depending on the layer, we have maximum aggregate size of 10 or 14 millimeter, followed by a foundation layer of 20 centimeter thickness of unbound material. Here you can see a schematic view of the different layers, and you can see that we have different thickness for top layer, collector, and base layer with different mixture. In the HEAL system, we also used support grid. But why? Because it provides us with exact pipe positioning. It can control stress concentration around the pipe, and it reduces machinery loads during the construction stage. We also sprayed bitumen emulsion between the pipe and grid and also for asphalt in order to improve the heat transfer, to have better adhesion with the asphalt mixture when we are placing it, and to have a allowable movement between pipe and asphalt since the thermal expansion will be different between the materials. Also, it is noteworthy mentioning that during the construction, we were circulating cold fluid through the pipes. And from the other side, we would have the warmer fluid coming out. The reason was to keep the pipes undamaged because of the temperature differences. In the right-hand side, you can also see a thermal picture of the construction after paving the asphalt. Regarding seasonal energy storage, the borehole thermal energy storages, or BTS, they are located next to cycle path. here in the picture. The aim was to store the extracted energy from the heel during summer for the winter time. We constructed 2 BTS with 100-meter depth for each. These systems drilled and sealed with thermal grout in order to minimize the heat loss between the borehole and the ground. And the reason was to prevent contamination of neighborhood aquifers. We also have temperature sensors in order to monitor the temperature changes in the asphalt pavement. We used ultrafine wire PFA thermocouples. We have 4 sensor sections. You can see in the schematic picture, we have 2 reference sections before and after the heel. And in the heat exchange section itself, we have 2 sections. In each section, we have 24 sensors placed. In total, we have 96 temperature sensors. In order to monitor these temperatures very carefully, in the heat exchange section, we have 8 sensors. At near surface, we placed 8 around the pipes, 4 sensors at the interface between collector layer and top layer, 2 sensors in the interface of collector layer and base layer, and finally 2 sensors in the middle of the base layer to monitor almost everything. All these sensors, together with flow sensors, inlet and outlet temperatures, and actuators, they are connected to a back-off terminal in the technical room, and they are logged. All the output data they are logged using a programmable logic controller PLC terminal. For the operational phase, our prototype is very flexible in its configuration. We have parallel configuration. You can see we can have 4 different sections working at the same time, or we can have a series configuration. It means that we can have one big circuit of pipes, or we can have combination of parallel and series. For the parallel configuration, for example, we can switch the 4 pipe sets all together at once. The reason is we can test having different flow rates at the same time. Then it means that we have 4 inlet going and 4 outlet coming from the heel system. Schematically, you can see here, it results in 4 50-meter pipe length for each set, 4 inlets going at the same time, and 4 outlet coming out of the system. In addition to this, we can activate the system in series configuration. It means that we can use the longest circuit and have 1 inlet going and 1 outlet coming from the system. This will result in 200 meters of total length of the pipe network. And schematically, you can see here, 1 inlet going and the outlet coming from the end of the system. We also can combine these parallel and series configuration together. It means that we can activate 2 parallel sets or 2 series of 100 meters. It means that we have 1 set of, I would say, series of 100 meters and have it in parallel with the other one at the same time. So we will have a combination of 2 configurations. Next to heel prototype, we also have a standalone weather station. In this weather station, we can monitor many different situations or weather parameters, such as relative humidity, solar radiation, wind speed, and so on. We also have a standalone data logger for this in order to monitor whatever is going on with respect to weather parameters. For the operational phase, this was one of the pictures from the test phase. After a couple of hours of running, we had this output. So you can see we monitored all the data and all the system configuration for these hours. During February also, we had almost harsh snow for Belgian weather conditions. We also monitored all the data for these days. And we can see that the project was successfully succeeded. I also took some pictures for the thermal pictures. I took some thermal pictures as well, as you can see in the right-hand side. We could also see or compare the configurations. For example, we had different flow rates going into the system, and we could see how they are reacting with respect to both weather conditions and, of course, the system configuration or system parameters, such as flow rate and the inlet temperature and so on. And these are the references that I used in my presentation. And thank you so much for your participation.
Thank you very much, Tahir, for this interesting presentation. I would like to remind everybody to please use the Q&A text box that you have in your platform to send comments or insights or questions for the speakers today. Our next presenter is Gudrun Golkowski. She's a civil engineer, deputy head of section Earthworks Mineral Aggregates in the Department Highways Construction at the German Federal Highway Research Institute, also known as VAST. Gudrun works on the topics of mineral aggregates and unbound granular layers in close cooperation with the topics of pavement structures and pavement design to implement research results into practice. Furthermore, she is a member in numerous committees for the development and revision of national guidelines. In the paper she presented, it is explained that the road performance is strongly influenced by the climatic conditions. Therefore, limiting the temperature range of pavement construction has a significant impact on its service life. In the previous presentation, we learned how to do this by using a pipe system with water inside. And in this case, we will learn about a different approach consisting of a porous polyurethane bond interlayer and its implementation on a new research area at VAST. Please, Gudrun, the floor is yours.
Dear ladies and gentlemen, today I'd like to inform you about the current research project on tempered road sections that will be realized on our quite new test section Durabast. The outline of my project is as follows. Firstly, I'd like to introduce you our new testing area Durabast. Secondly, I'd like to present you the research aims and the tempered road section itself. And finally, I want to inform you about the data monitoring and the energy system we use. So, what is Durabast? Durabast is our new demonstration, investigation, reference area of BAST, and it's placed in the middle of the motorway junction of Cologne East. At Durabast, investigation test section and demonstrators enable realistic full-scale tests. And so the time required from the idea of an innovation to its standard application can be thus significantly be shortened. So the reference sections have sections with texture, with transverse evenness for skid resistance, longitudinal evenness, and also for substance characteristics. The demonstration and investigation sections are placed quite in the middle of the test sections. And furthermore, we have a bridge in this area, which is equipped with different sensors. So we use this bridge for bridge monitoring. The tempered road sections will be installed right in the middle of our test sections, and the energy system will be installed directly close to it. So what are the research aims of our project? Firstly, we want to demonstrate the functionality of tempered road sections. We want to install an automated control and regulation of the system. We want to evaluate the efficiency of the temperation. And based on all those findings, we want to derive an analytical design method for tempered roads. The sections will be subdivided into 5 subsections and the energy system. The 5 sections, 2 sections will be equipped with pipe registers as a standard temperation system, and 3 sections with an innovative porous bound interlayer. So the two pipe register sections. All our test sections are referenced to a standard or German standard of the RSTO. It's we choose a loading class of BK 3.2, which means the upper structure is meant to last for 3.2 million 10 tons axle overruns within the lifetime of 30 years. We will have a two-pipe system with helical lines, and we also will have a single-pipe system with serpentine lines. The pipe registers are embedded into a 4 centimeter mastic asphalt course, and they will be covered by a 3 centimeter mastic asphalt wearing course. And the other 3 sections will be equipped with our innovative porous bound interlayer. But what is a porous bound interlayer? The porous bound interlayer is placed on the asphalt base course, and it is covered by a mastic asphalt course. The characteristics are: it is open graded and polyurethane bound. So we don't use any bitumen because bitumen is highly sensitive to air and water. And the structure of this porous bound interlayer, it has a very high void content of over 30%. And furthermore, it's highly permeable. So how does the tempering work in this interlayer? We have the structure, and in the tempered layer, we introduce the tempering fluid through pipes. The fluid passes through the layer and will be collected in many folds at the other end of the pavement and will be recirculated to the energy system. So we will have 3 different sections with porous bound interlayers. They are also referenced to our standard. And we will have a 5 centimeter interlayer with a gradation of 0 to 8 millimeters grain size. The second sections will have the same thickness, but we will use another mixture, another gradation of the mixture. And the third sections, there we want to use the same gradation of the mixture, but we will have another thickness of the pavement. To evaluate the efficiency of the temperature or of the tempering of the road sections, many sensors will be installed into the systems. The position of the different sensors strongly depend on the type of the pavement. We will have 3 or 2 sensors over the height of the pavement, and we always want to have sensors on the warm side of the temperation and the cold side. And you see it on the floor plan how the sensors are distributed. In addition to that, we will also have a reference sections without any temperation to monitor the temperatures. As energy system, we wanted to use geothermal probes, but due to the situation close to Cologne, there are still many bomb fonts in this area due to the Second World War, so sinking boreholes is still a danger. And furthermore, our research project has only a restricted lifetime. So we decided not to use geothermal probes, but to use standard heat exchangers for tempering our road sections. The energy system itself, it's also equipped with a lot of sensors. We will have temperature sensors at the in and outlets of the energy system, as well as on the inlet and outlet of each pipe to the different road sections. Additionally, we will have pressure sensors and also heat meters. To conclude my presentation, I just want to recall the research aims. We want to demonstrate the functionality of the different sections, especially of our innovative porous bound interlayers in comparison to the standard pipe resistors. We want to show the efficiency of the temperation in combination with an automated regulation and control of the energy system. And we want to use all our findings to derive an analytical design method for tempered roads. So the last thing for us, but not least thing, is to press the button to start our project and to start tempering the roads, hoping that the scientific project makes more than just boing. Thank you.
Thank you. Thank you very much to these first three speakers. What a nice way to start this session. I would like now to call Christoph, Taher, and Gudrun. Maybe you can turn on the cameras and we can have this Q&A, because I have been receiving some questions. I have my own questions as well, because they were super interesting presentations. Christoph, since you were the first, I would like to ask you a question.
Yes, sorry, I cannot turn on my camera because apparently the animator has stopped it.
Okay, while we solve that, maybe Christoph.
Okay.
So you mentioned a benchmark study on the road, how the road mobility can impact the infrastructure. Yeah. I have a question. Is this study including as well how the new mobility, how the new users can impact the durability itself of the infrastructure?
Yes, it does, in the sense that, as I said during the presentation, the modification of the behaviors in the usages of the road will have an impact on the way we conceive it. And so it will also have an impact on its sustainability. We won't build or maintain or improve or modify the infrastructure the same way we have done for many decades in the past. We will have to consider other criteria. Obviously, what the different types of users and the new users, let's call them like that, are expecting from the road infrastructure. And we also have to fit into the broader framework of making the whole mobility more sustainable. And there's a lot of contribution that the road can have for making mobility more sustainable. And we need to insist and keep on saying how good we are to contribute to this better, more sustainable, greener mobility, and that we are not the sort of bad component of the mobility like some people would like us to show us, and we definitely can bring a lot to improve the sustainability of mobility. We are the main mobility vector anyway. So
thank you, and I can't agree more. Actually, at the EAPA, we're also trying to identify potential damage that new users, or how new users could accelerate the damage of the road, just to be ahead and then maybe shift to new designs or so. But yes, thank you very much. And in this line of the maintenance and durability, I have some questions. So, for example, for Taher, Hitoshi Yamauchi is saying, thank you for your presentation, very interesting. He's asking, the required energy to melt ice, snow, while winter was fully covered with the energy stored. Was that enough?
Yes, if I would like to continue here. The thing is, based on our analytical calculation, like in the initial phase, we knew that in the location or in the geography of Belgium, we will have more than enough. Also, we thought about spreading or like outsourcing the rest of heat to district heating network after summertime, because probably we will have more than enough heat collected in the summertime. So based on our expectation, based on the weather parameters we expect in Belgium, we calculated in the last 5 years, almost we will cover it. So even if we need more heat, we have another heat pump in our system. So the extra energy that we need or extra heat we need, we will use it as support from the heat pump.
Thank you. Can you tell us what is the material of the pipes and how this can interact with the asphalt layer when having thermal expansion? Or
the material is polyethylene tubes, and as I mentioned before, we have support grids in the pavement as well. So the idea of actually expansion is when we send higher temperature of heat. Normally, this is low temperature heat that we will extract and feed the system. But for any research reason, if we increase the heat, probably there can be thermal expansion between the material and also asphalt. So we also thought about that to use emulsions and spray between the pipe and grid, of course, between also the asphalt layers.
Thank you. We have also a question for you from Mike Southern. Do you have any feeling for the amount of energy collected during the trial? If there were a fracture in one of the pipes, how could you identify where the fracture was? I think that's a question.
That's one of the major issues actually for the maintenance and also like the risks. I have actually not much ideas about how to detect that leakage, but of course we can know that the leakage happening from the pressure drop into the system. We know that there is leakage, but where to find it, at least in our system, we know that because it is a closed pipe, closed circuit, so we can close just one of them and know which pipe section is actually has leakage or damaged, and just turn it off. So normally we can handle it easily. But for the maintenance, this is one of the major issues, how to take it out of the system if you use long pipe networks. So then there should be like a balance between the pipe length in the system and also the maintenance in practice, like how to deal with it.
I think you already answered also another question we have for Christina Smith. In the last session, Steve Phillips said that the road owners were nervous about maintenance issues related to like yours. What are the risks in this respect? And I guess that's,
yes, mostly, as I mentioned, it's leakage, but more than that, I think we believe that structural damage is also one of the important aspects that should be studied, as I mentioned in one of the slides. So there should be a balance between the amount of energy that you can harvest and also like the closer pipe you bring to the surface of the asphalt, the more you are bringing it to the potential of damaging by the structural loads, of course.
Okay, thanks a lot. And I have some questions for Gudrun. Why choose polyurethane for the interlayer binder? Did you test other polymer, or is this the optimum, or just the first step?
Yeah, we have some experience with the polyurethane bound interlayers because we had other projects. So our focus was to have a construction without any pipes. And the advantage of this polyurethane bound interlayer is that we really have a very high void content, and it's very permeable for the tempering fluid. So our first focus is to show that this type of layer is working properly with tempering. Using polymer bound layers was not in the focus, but if this type of construction with those permeable interlayers, probably it could be a second project to compare those polyurethane bound to other polymer bound interlayers.
What about recyclability? How can we, at the end of the service life of these roads, can mill the whole material? I don't know if we have to go layer by layer very accurately. I don't know if this polyurethane can somehow contaminate the rest of the reclaimed asphalt that we obtain from the road. Do you have any thoughts about that?
Yeah, we have, of course, looked at it before. Of course, you have to mill the layer separately, but the PU or polyurethane bound interlayers, it's easy to mill and it's easy to reuse. So you can use this material again as a polyurethane bound interlayer, and you don't have any pipes or any other things in the system, which makes recycling much more complicated.
Okay, thank you a lot. I would like to continue with the next three speakers because I would also like to leave some time at the end of the session today for them as well. So please keep sending questions for the speakers. If not now, we can also continue the discussions in the networking area of the Congress. So thank you a lot. Thank you very much to these first three speakers. And we continue now with the next presentation. It's called Perpetual Road Pavements with a Graphene-based Super Modifier. It will be presented by Shahin Eskander-Sefat. He is a senior researcher at Iterchimica, Italy. He received his PhD in civil engineering at the University of Bologna in Italy, 2019. During the past decade, his work has been focused on investigating and developing sustainable road pavement solutions. He has authored several peer-reviewed articles on asphalt pavement materials and management, and he is a very active member in our EAPA technical committees and task forces. Today in his presentation, Shahin will provide the laboratory and in situ test results of a test track in Rome, Italy, where an innovative asphalt modifier made of graphene nanoplatelets has been used. Please, Shahin, the floor is yours.
Hello, everybody. My name is Shahin Eskander-Sefat, a senior researcher in Iterchimica, and I'm going to present a paper entitled Perpetual Road Pavements with Graphene Enhanced Super Modifier on behalf of a research team. What you will see in this presentation is consisted of a short introduction on this research project. What is graphene nanoplatelets? What has been developed in this project? Our test results during our first trial section in Italy consisted of both lab scale and in situ test results, and finally conclusions. This research was a European Union research entitled EcoPave, and with the goal of to develop an innovative asphalt mixture super modifier to be used in asphalt via dry method. 4 different partners were collaborated in this research, consisted of Iterchimica, Diritto Plus, GECO, and University of Milan Bicocca. And what has been developed in this project was a graphene enhanced super modifier, mainly consisted of technically selected hard plastics, functional based polymeric additives, and graphene nanoplatelets. But what is graphene nanoplatelet and why it has been used in this asphalt super modifier? Graphene is a single monolayer of carbon atoms organized in honeycomb structure. According to the existing literature, it has been shown that the addition of 2 to 5% to plastics and resins, they can improve significantly the mechanical and performance properties like as strength, stiffness, and surface toughness. Here you can see the plot showing the trial section has been done during this research. This trial section located in Italy, in Rome area, via Ardatina. The trial section consisted of both bearing course and binder course. Here I'm going to represent just the bearing course test results. And as you can see in this plot, the trial section was divided into 4 different sections. The first graphene enhanced super modifier, and the second SPS modified mixture, and the third was a comparable elastomeric polymeric compound modified mixture, and finally the neat bitumen. The mixture was of dense graded asphalt mixture, and the bitumen was of 7100 bituminous binder. And the dosages, as you can see here, 5% was for the graphene enhanced super modifier, 3% for the plastomeric polymeric compound, and 5% for the SPS modified mixture. The testing plan included both in-situ test and lab scale test. During the in-situ tests, we have used heavyweight deflectometer, and during the lab scale test, the mixtures were investigated by means of modulus, fatigue endurance, and resistance to permanent deformation. During the Institute test, the heavyweight deflectometer has been done at 20 degrees centigrade, more or less the temperature. And according to this table, you can see the modulus of the mixture containing graphene enhanced supermodifier were almost double when compared to the neat bitumen, and comparable and or superior for the other two tested mixture in this study. And continue by the lab scale test results. The first test was indirect tensile stiffness modulus. That has been done according to the European standard number 26. The test was done at 3 levels of temperatures, 5, 20, and 40, representing low, medium to high temperature, respectively. And according to this plot, you can see that thanks to the presence of this graphene enhanced supermodifier, the stiffness modulus of the mixture at all the 3 levels of tested temperature were higher. The second test during the lab scale investigations was permanent deformation. Here you can see that according to this table, the permanent deformation for the mixture containing graphene enhanced supermodifier were superior when compared to the other tested mixtures. This could be expected since during the ITSM modulus testing and HWD Institute testing, we have seen higher stiffness for the mixture containing asphalt supermodifier. And the last test was fatigue endurance that has been done according to European standard number 24 by means of indirect tensile fatigue test. And you can see according to this plot, the mixture containing graphene enhanced asphalt modifier showed significantly better results when compared to the reference neat bitumen, and comparable or better results when compared to the commonly used SPS modified mixture. And conclusions. Here in this early stage trial section in 2090, HWT test results has been done, and according to the test results, we have seen almost double modulus for the mixture containing the graphene enhanced asphalt modifier. The thermosensitivity of the mixtures were investigated by means of ITSM modulus, and as it was seen in the HWD investigations, the mixture containing super modifier showed a significantly higher modulus when compared to the other 3 tested mixtures. And as expected, it could be expected, the testing results during the permanent deformation showed better results for the mixtures thanks to the presence of graphene and nanoplatelet, graphene and nanoplatelets, graphene nanoplatelets in this mixture. And finally, the resistance to fatigue of the mixtures were compared by means of ITFT. And the mixture were significantly showed better results when compared to the neat bitumen mixture with considering 250 kilopascal as a common medium level of stress for fatigue investigations. The mixture showed 60% higher and better results for the mixture containing super modifier, and significantly better results compared to the other plastomeric mixture. Thank you for your attention and join hands to save the environment.
Thank you very much for this presentation. I would like to say before introducing the next one that we are receiving a lot of questions for Shahin. So I don't think we will have time for all these questions. So please vote for it, like them if you like any particular question, so it will help me to identify the questions that are most interesting for most of the audience. With that, we reach the last presentation. This will be, the title is Fiber Drag Creatine Monitoring System for Heavy-Duty Pavements. It will be presented by Patricia Cara de Maya. Is a civil engineering and carries out research in the Energy and Materials in Infrastructure and Buildings Research Group at the University of Antwerp in Belgium. Patricia's main research areas are fiber brack grating, sensors monitoring systems, concrete technology, asphalt and bitumen, and recycling of industrial wastes and byproducts. Patricia is a senior member of RILEM, has co-authored more than 60 scientific publications, and recently she has edited the book titled Recent Advances and Future Trends in Pavement Engineering. Her presentation today is about innovative solutions for monitoring of heavy-duty pavements in real time by means of fiber brack grating sensors, which has been tested in the field. A brief summary about the installation process, monitoring campaign, and results will be given during her presentation. Please, Patricia, the floor is yours.
Good afternoon, ladies and gentlemen. The theme of the presentation is fiber brack grating monitoring system for heavy-duty pavements. I would like to start my presentation from the quotation of Professor André Molenaar, saying that monitoring of the pavement is an art, and it's true, and it's a very complicated issue nowadays. And the installation of strain gauges in road structures is practiced for several decades already, and getting more advanced along with the technological progress. Here to your attention are the examples of successful installations, for example, carried out in TU Delft in the Netherlands, Laval University in Canada, IFSTAR in France, Federal Aviation Administration in USA, Kajima Technical Research Institute in Japan, Dalian University of Technology in China, Hwt in the Netherlands, and U Antwerp in Belgium. A fiber brack grating is a distributed mirror in a short segment of an optical fiber that reflects a limited wavelength range and transmits all others. The working principle is based on a periodic variation of the refractive index of the fiber core, which acts as a wavelength selective filter with a central reflecting wavelength. The sensing information is encoded in the optical spectrum, which is reflected by the fiber brack grating. An external perturbation, for example, temperature, strain, causes the central brack wavelength to shift. Like, for example, here on the figure, you may see the fiber brack fiber and fiber brack grating, which for sure is not invisible. But whenever you push on this spot, you might see following event, which is a strain shift or temperature shift. Due to the complex characteristics of pavement structures, few available references provide definitive specifications on their mechanical properties. Installation of fiber brack gratings in asphalt pavement is a rather sensitive matter. It requires understanding and field expertise on how the materials work together in order fragile, high-tech fiber optics can handle harsh and rough environment during asphalt pavement constructions and its service life. The first FBG monitoring system prototype was installed at University of Antwerp in 2017 in the bicycle path cypads, when two installation methods were applied. One was in prefabricated asphalt samples, something similar to the idea of research from Kajima Technical Research Institute in Japan, and just sewn in grooves at the bottom of the asphalt layer. The survival rate of the sensors was 100% during construction and 60% during service life. Here you might see the scheme of the installation. So at the bottom layer, there were 16 sensors, and at the following layers, there were randomly just few sensors. And falling weight area was applied in the middle of the road. The second FBG monitoring prototype was installed in a heavy-duty pavement in the port of Antwerp in 2019. The design of this sophisticated system with strain sensors oriented in longitudinal along the drive and transverse directions. With temperature sensors at each road structure layer was elaborated together with common sense, and it was successfully placed. However, facing real construction of heavy-duty pavement and traffic, the system had to undergo significant sensors loss, which mostly was related to difficulty of installation of sensors in GeoGrid and in the prefab element. Considering that difficulty of installation of FBG sensors in prefabs, the alternative solution was tested in Test Blauweg in Port of Antwerp last year in December. The installation was performed directly on the unbound base layer when FBGs were placed in groove in the mortared area, and 2 mortars were tested, cement-based and epoxy-based. The survival rate showed 100% of sensors to be survived, and temperature sensor was also placed next to the area, and this installation mostly meant for performing falling weight measurements. The advantages FBG system proved to be successfully installed without sawing the whole asphalt layer in 2 parts. In general, these systems can be continuously monitored at each layer of the road structure for a long period of time, during all seasons. However, long-term monitoring brings along big data files, which require sufficient and time-consuming data mining and storage space. In regards to advantages of installation, it shows that the best installation can be carried out in grooves. In regards to the disadvantages, FBG monitoring systems are very sensitive to loss of sensors, and in particular it's GeoGrid level, and prefabs are not really suggested for the installations. Here, for example, you may see what was the total sensor loss during installation 2019. We lost mostly 50 sensors, and mostly they were related to GeoGrid and prefabs. And there were no loss sensors, for example, in surface layer. Also, during service life, you might lose several sensors. 2 types of monitoring campaigns were applied: falling weight deflectometer measurements and heavy loaded traffic monitoring. When measuring pulse time of FVD measurements and matching it with FBG sensors response, there is observed a very good fit at the high frequencies for signal processing, when strain value can be clearly extracted from the measurement. The FBG peak shape and pulse time are identical to falling weight, as you can see it here. When measuring deflections, there is a possibility to back calculate E moduly and compare it experimentally, which normally is well-established procedure and provides corresponding results. And having a good engineering developed models to estimate the tensile strain occurring at the bottom of asphalt pavement layers, for example, proposed model by Bilodeau and Doré in 2012, there is a possibility to compare calculated strain values from FVD to measured from FBG. And here you might see that the correlation is 6% of deviation. The continuous monitoring was the reason for the development of the complex script pavement to process and analyze big data from the monitoring campaigns that is further developed to have a user-friendly interface and easy way of the information overview. Here will be a little example of data for 1 truck passing over system with indicated overload. For example, here you might see the extraction of 1 truck passing And here it says that it has 4 axles, and one of the axles is clearly overloaded. Performing continuous monitoring of the pavement, there is a possibility to have an overview of the applied strain values and its intensity over the time, which normally have to be below 50 microstrain. And here you might clearly see that some of the asphalt layers are overloaded. Performing continuous monitoring of the pavement, there is a possibility to the variation of the temperature in different asphalt layers and asphalt types. Design of 3 FBG monitoring system prototypes, SIPADS, BWDZ and Blauweg, was elaborated and tested. The outcome of this work will be applied in the simplified installation of FBG sensors configuration in the next 4 test tracks in the port of Antwerp. Thank you for your attention.
Okay, thank you, Patricia. Thank you for this excellent presentation as well. I would like to call now Shaheen, Patricia, yourself, and Marcus for the last Q&A. So I have received several questions for Shaheen. I would like to start with him. In the meanwhile, please, you can keep sending questions as well for Marcus and Patricia. So Shaheen, have you evaluated the workability, compactability of the graphene modified mixtures? Any difference compared to the rest of the mixtures? You also have another similar comment is, did the road constructors notice any difference in the material when they were laying it?
Well, first, let me thank all the attention and all the interest to this job. And I would like to draw your attention that, as I was saying, this project was the European Regional Development Funded project, which has been developed more or less 5 years ago. And this result was the first trial section that was installed using this new additive developed during this research project. What I'm going to respond to this question is based on all the outcomes from other also 10 trial section, all in Italy and in UK. Also, we had installed 3 pavements in UK, and I would say if the production was followed, the production procedure was followed according to our instruction, the correct temperature, you know that we are talking about the dry method application of additive, not wet method, that bitumen is already modified and is used in the for the production of the mixer. So the temperature is of utmost importance. So if you keep the temperature at the required one, and also during the compaction and at normal normal asphalt, PMB asphalt, no, we haven't, according to this 11 trial section in different for different application, never seen any big issue, let's say, or difference, tangible difference between regarding the volumetric parameters.
Okay. Can you tell us a bit more about how you mix how you blend the graphene and to make sure that it's well dispersed and everything? So how do you add the graphene to the binder?
Oh, very good. It's a very good question, but I'm not sure how much I can explain about this, but because the point is that almost all the latest research showed that the application of this nanomaterial, especially we are talking about graphene, has a very great influence on the properties of especially binder. So as perhaps you and many of the audience know that the problem was the dispersion, the homogeneity of the additive, and for this reason, actually, we use this graphene into this combined with other constituent of this additive to make sure that we can disperse this very small quantity of nanomaterial with this scale into throughout the structure of the asphalt pavement. And I would like to mention that even this procedure has been patented. So unfortunately I'm not able to go further details to explain how exactly we use this the nanoplatelets into this, but I would like to say that the type of the nanomaterial was used and nanographene was used was very important, because we have tried, for example, tubeless or nanotubes or different types of nanomaterials, but we reached to the point that this special type of nanoplatelets graphene is the best choice to be used.
In this regard, I totally understand. To be honest, I've never had graphene in my hand. I don't even know exactly how it is. Have you detected, because I think you mentioned that you are using a dry system to add it, have you detected any potential concern in terms of health and safety, or like dust generation,
No. But please consider that this additive is consisted of other also two different additives. So there are also another very important thing is that most proportion of this additive was hard plastics. And not normal plastics, but hard plastics. So we applied a very special procedure to mix, let's say, this graphene, these hard plastics, and these plastics have been never used in road. I would like to draw attention of you and also the audience that these plastics never been used in any other work in the road construction of the roads. We use these hard plastics and other additives in addition to the graphene nanoplatelets and make plates. And these pellets were added to the hot aggregates before adding the bitumen, both during the lab production and also in the plant production. So you have pellets of this or granules of this additive. You are adding it to the hot aggregates.
Okay, interesting. I think it would be good to have a look at that as well. And maybe
just because I understood that there are several questions, that please find out our new publications. There are much more news about this, because this paper was for 2018, our first trial, but now after 11 trial section, we have reached very, very interesting results, maybe of all interests.
Okay, thanks a lot. I would like to dedicate some time to the other presenters. So Marcus, we have a question in general to all the projects on energy or heat exploitation. Have you assessed, or do you have any preliminary study on the energy return on energy investment on the harvesting system?
Yeah, yes, this was different. The hardest part to evaluate. The goal of this project was to use the thermal energy and produce electricity. So we used an organic ranking cycle to convert this energy, and we estimate that there's an energy use of maybe 5 to 6% for this special test area in Cologne. So the problem here in Germany is that you not have so much hours per year where you have so really high temperature. So you get a fluid temperature for more than 40 degrees. So it's a little bit difficult. But when you shift this method or this construction to other countries, I think there's a high potential to use it.
Mm-hmm. Did you notice or take into account the higher stress and lower compaction degree of the asphalt around the pipe network?
Okay.
Identify some tracking thing there, some criteria.
We test this during this research project. The pipes were embedded in an area in matrix asphalt in this base layer course, and so we test here some samples in the university. We put some asphalt, or this pipe in an asphalt, and tested this in the long-term triaxial test. So we have, I think, more than 1 million cycles, and then we cannot find some errors or some failure in the pipe, and also not in the pavement. And the second test was in this robust test area. At the end, there was some tests in a higher scale. The BUS, the German Federation, have some test machine, and then they tested also in long-term uses. And we found some deformation and we found cracks on the surface, but the pipe collector still was usable and there was no leakage in these pipes. So I think it should resist. So it's a little bit difficult to generalize this because we minimize the thickness of all layers. So we construct these test areas so that we can get some failures during these tests, but we cannot see it in real. So maybe it works better than we expected.
Thank you very much. And finally, I would like to also address Patricia. We have a comment saying that in your list of instrumented pavements, you forgot the world-renowned MN Road facility in Minnesota, USA. So just a comment in this regard. And I have a question for you. So a question that actually applies to all the systems, all the Steve put in roads and your sensors as a part of that as well. And is, first of all, how do you see what we can do when we want to remove them from the road, or when we want to do any recycling operation at the end of the service life? How we can get rid of them? How they're going to affect the milling operations and so on?
Well, in general, these sensors fibers are very thin. It's like 1 millimeter fiber length. If you recycle it, I think it will have a minor effect. Depends for sure how many of the sensors you use in the road. If you use a really complex system like we had the second prototype, well, it might have some effect, but in general, I think that should not be a problem. And it's just recycled as general asphalt.
Okay, probably
yes. More difficult structure in asphalt, like pipelines and everything, yeah, then it's a different issue. For these fibers, it's really minor, I think.
Yeah, well, I think
for my colleagues, it will be interesting to do in the future.
We are now in the times of the circular economy and everything. So everything that we put in asphalt should be considered how we are going to end up recycling at the end of the service life. We have a material that is 100% reusable and recyclable, and we have to make sure that whatever we put in there, we preserve this characteristic. I have a lot of more interesting questions, but unfortunately we have no time. We have to close the session here. Thank you very much for all the participants in this session, for the great discussions, and thank you, of course, to all the presenters, for the papers, for the great presentations we have today. It's been a pleasure, and I really hope that everybody enjoyed this session as much as I did, and that enjoys the rest of the Congress as much as I'm sure I will do. So thank you very much, and we close the session here.
Thank you.